What about the potential? We just calculated the potential energy of 2 particles. What about if you have more than 2, 3, 4, 5, any number of particles that you have? That is, you want to calculate what's the potential energy of, say, this configuration of particles. Call this one Q1, Q2, Q3, Q4, Q5. And I'm going to draw a line here to say this is the system that I'm looking at. And I want to calculate how much is the potential energy of this system. It should have some potential energy, of course. If they were all positively charged, for example, you know that if you let go of these particles, they're going to repel each other, and they're going to gain kinetic energy and move away from each other, so that energy had to come from somewhere. So you say, well, that energy came from the electric potential energy that they had at the beginning. So how much is that potential energy when you have more than 2 particles? The approach that you can follow to figure out how much is the potential energy is to take 1 particle at a time. So start with these particles, because remember, we just discussed that the work done by an external force to assemble a system of charges is equal to the potential energy of the system of charges. Right? When you have finished putting them in the location that you want them to be. Okay? So if we use that equation, we can start building this system 1 charge at a time. So take them, all of the charges at infinity, bring 1 to some location in the universe. Since they're all at infinity, that you didn't have to do anything, just pick 1 and that will be the center, or the initial one. So take Q1 somewhere, the rest of them are infinity, and now take Q2 and move it from infinity, bring it to the location that you want it. How much work did you have to do that? The work that the external force had to do to assemble the system 1 and 2 will be equal to the potential energy of the final configuration. The potential energy of the final configuration is K Q1 Q2 divided by the distance between 1 and 2. Right? 1 and 2 have a distance like this. This is R1, 2. So we're going to build this thing 1 at a time. So you have put in the system this much energy. That's the work that you had to do. Now once the 2 are in place, take a 3rd particle, which remember that they're all at infinity, and bring it to the location that you want it to be. So you bring it from infinity and you place it here. How much work did you have to do that part of the process? How much additional work, right? So now it's the external work that the external force had to do to now assemble the additional work that you have to do to assemble now to bring the 3rd particle close will be equal to what? Well, the force that the external particle is going to have to apply to this to bring it from infinity is going to have to cancel the force at all times. Is going to have to cancel the force of the interaction between 1 and 3 and the interaction between 2 and 3. Right? At all times, 1 and 2 have been repelling. Let's say that Q3 is positive, they're all positive. At all times, 1 and 2 have been repelling 3, so the external force had to be pushing against the electric force between 1 and 3 and between 2 and 3. Correct? So the external force has the opposite sign. I'm going to write the details, but it will be easy for you to figure out that that's going to be equal to KQ1 Q3 divided by the distance 1, 3, plus the term that has to do with the interaction between 2 and 3. Both 1 and 2 are already a location, and they're pushing away 3. So you have to do this work to assemble 1 and 2. To bring 3, now you have to do a work that has 2 terms. To bring 4, now you're going to have to fight against 3 charges that are repelling 4, so that's going to have 3 terms. So when you're done with this process of assembling this system of 5 or whatever number you have, the work that you will have done will be equal to K, Q1. You're going to have to add all those works. That was the work to assemble 1 and 2. The work to assemble 1, 2, and 3 additional to bring charge 3 nearby is this. To bring 4, you're going to have a few more terms here. So the general expression that you can write is this. Remember that this is going to be equal to the electric potential energy of your system. Because when you're done doing all that work, you have put all that energy into potential energy. So the potential energy of a system of charges can be written like this. What you end up having is the sum of all of the possible pairs of charges, 1 with 2, 1 with 3, 1 with 4, 1 with 5, and then 2 with 3, 2 with 4, and so on. So you can write it this way. And the notation here, I smaller than j, means that you're not going to, if you count 1 and 2, the potential energy between 1 and 2, you're not going to count 2 and 1, the potential energy between 2 and 1. It's the same thing, right? We already counted that. It's the interaction between 1 and 2 has some potential energy. So that's why you're placing, or you're writing j bigger than I. So you take 1 with 2, 1 with 3, and you're not going to count 2 with 1 or 3 with 1 again. So in a little sketch, what you can, the way to figure out all these pairs quickly would be just write your charges as 1, 2, 3, 4, and whatever charges, as many charges as you have in your problem, and you start doing pairs like this. Take 1 with 2, 1 with 3, 1 with 4, 1 with 5. Now you don't want to go back and take 2 with 1 again, so you move forward starting from 2. So 2 has interaction with 3, and 2 has interaction with 4, and 2 has interaction with 5. Now you move on to 3. You don't want to count 3 with 2 and 3 with 1, so you move forward 3 with 4 and 3 with 5. When you move on to 4, there's only one interaction that has not been accounted for, is 4 and 5. Okay? So that will be a way to make sure that you have counted all the pairs. So this sum is over all different pairs. Every different pair that you have will add to the potential energy of the system. You will add a term to the potential energy. And those distances, of course, you're going to have to be careful about the distances, because what goes in the denominator of each one of those terms is the distance between the corresponding pair. So this is the distance between 1 and 3. This is the distance between 1 and 4, and so on.